In an arrangement shown in the figure, the ends P and Q of an unstretchable string move downwards with uniform speed u. Pulleys A and B are fixed. Mass M moves upwards with a speed 2u cos theta, u by cos theta, 2u cos theta and 2u by cos theta and u cos theta. Okay. First of all, you have to understand that this is a problem on dependent motion. Correct? This is a problem on dependent motion. And we know now, okay, because the string is unstretchable or inextensible, the total length of the string is always going to remain constant. When we were revising the things, I told you that the main equation in dependent motion arises from that fact. Okay? Now what I am going to do is, I am going to draw a larger figure here so that we can show the details. Okay? Yeah, okay, that much is enough. Okay? Fine. Now, see, let us choose this point O as origin. Okay, let us choose this point O as origin and let us select the vertically downward direction as y-axis. Okay, rather let us call O to M as y. Okay, O to M as y. And suppose I call this as x. Okay, suppose say I can also call OB as x, but because Q and P are moving downwards with uniform speed, both P and Q, okay, we are well, we can take any of the two, okay, either this or that. Fine. Now, if I consider triangle OAM, if I consider triangle OAM, can I say that AM squared for all instances is equal to OA squared plus OM squared? Yes, that's simple right triangle trigonometry. So let the length of AM be, okay, let's call it R. R squared is equal to OA squared is x squared and OM squared is y squared. Now can you tell me, during the upward motion of M, which of these three quantities remain constant? Does R remain constant? Does X remain constant? Does Y remain constant? X remains constant. So let us differentiate this. Apply chain rule. 2R dr by dt is equal to 2x dx by dt plus 2y dy by dt. Now what are they saying? They are saying that pulleys A and B are fixed. Okay, pulleys A and B are fixed. So because pulleys A and B are fixed, dx by dt is 0. As pulley A is fixed. Okay, as pulley A is fixed. Now you also find that the derivative of y with respect to t also gives me the velocity, instantaneous velocity of M, right? So let me first cancel 2 here and I can write dy by dt as r by y dr by dt. Okay, now they do not have the variables r and x here, they rather have theta. Now consider triangle AOM. Cos theta will be y upon r, right? Cos theta will be y upon r. So r upon y will be sec theta. And what is dr by dt? Now look, dr by dt tells us, okay, how fast is how fast is the length a to m decreasing, the distance a to m is decreasing, correct? And because these pulleys are, well, we can assume them to be smooth and there is no sliding happening, so the speed of rotation of this is such that any point on its circumference will have the same linear speed equal to r omega. which is equal to V or U, sorry, U. Okay, so it will be U sec theta or U by cos theta. Okay, U by cos theta. So the correct option is B. Now you might be wondering, what is the purpose of the second pulley then, right? Should it not be 2u cos theta, because we did not consider the motion of the other pulley also. Now just imagine if I break this, okay, if I break this, then how would the arrangement look like? If I break that, then the arrangement would look something like this. Isn't it? If I break that, the arrangement would look like this. And you know how to handle these situations now. Correct? You understood this, right? So that is not 2u sec theta. It is only u sec theta. Any doubt? Understood? Great. Now, we use this property of right triangle and its applications in ladder problems also. Well, because we have now used that, we sometimes use it in ladder problems also, not exactly ladder friction, but ladder problems. Okay, you may have solved problems of the following kind. Okay, a ladder rests on with the support of a wall. Okay, a ladder rests like this, its length is L, and suppose this end is pulled with some speed Vx, suppose. They ask us to determine the length, the speed at which the other end of the ladder moves downwards. So even here we use the same formula. What do we say? We say let this have x coordinate x, let this have y coordinate y, and in this case we say x squared plus y squared equal to L squared. But unlike this problem, the dependent motion problem where OA remains constant, in that problem ladder sliding AM remains constant. Okay, AM remains constant, so we just have 2x dx by dt plus 2y dy by dt equal to 0 again. So if we want to find Vy, we can just say x Vx plus y Vy equal to 0, and depending on the values of x, Vx and y, Vy can be determined. We quite often do not appreciate that this is actually a vector equation. Have you ever realized this? It is actually a vector equation. There are two things which are undergoing rectilinear motions here. Which two things? First is the motion of the end of the ladder which touches the ground, and the other one is the other end of the ladder which touches the wall, which slides down along the wall. Is that clear?